In the previous slides, we talked about a couple of different traversal algorithms. And now we can think of another operations for binary tree. So first one is copying binary trees. So given a binary tree, like we have lots of nodes in a tree, and then we declare another instance of binary tree, and initially it is empty, and we want to copy the original binary tree to a new one. Okay, so think about this one. When we copy a tree, then we have to follow all the nodes. We have to traverse all the nodes, and at the same time, we have to allocate memory space for all the nodes, and we have to copy the data. We'll talk about this implementation in the following slides. Okay, next one is testing for equality of binary trees. Given two binary trees, are they the same? Okay, so we want to check all the nodes. Okay, so basically the structure should be the same and the data should be the same. Okay, and then next one, we will not cover these satisfiability problems in this class, but let me briefly mention what it is. Okay, satisfiability problem means we want to ask whether we can make an expression true. Okay, so there is an expression like this. So we have a simple example here. So we have three variables with AND operation and OR operation and NOT operation. And since we have three binary variables, then we can think of 8 different combinations, right? So with this expression, we can think of a tree. Okay, so we can use a binary tree. And with this binary tree, then we can actually apply 8 different configurations of these binary variables. And then we will see, we will evaluate these expressions. And then we'll see any of these 8 configurations could be true. If there is a true, then this expression is satisfiable. But if all the configurations are false based on this expression, then it's not satisfiable. Okay, so basically we can use a tree structure, binary tree structure, for this satisfiability problem. This is what this item means. Okay, the next one is not an new operation. It is actually the same thing. In the previous slide we talked about in-order traversal, so we talk about the same thing here, but in a different way. So can we implement in-order traversal without a stack? And it's possible, but it's really complicated, so we'll not cover that. If you're interested in, then you can search Morris traversal algorithm, but we'll not cover that in this class. Before talking about the copying and testing operations, let me briefly mention what functional overloading is in C++. In C program language, we cannot have different functions with the same name, right? But in C++, we can have a couple of different functions with the same function name, as long as their parameter types are different. Okay, so here in this slide we have 3 functions, member functions with the same name. Okay, print, but their parameters, the type of parameters are different. So first one has just one integer, and second one has one character, and the third one has one float. Okay, so we can define these functions in a different way. It looks the same, but you can define in completely different way. Okay, so in a caller function like main functions, once we declare an instance of this class A, then we can call a.print in different ways. So when we call a.print, we can pass 3 or 1 character or 1 float. Okay, if we call print with the integer 3, then the first functions will be called. Okay, and if we call a print function passing 3.14, then the third function will be called. So the reason why we have a function overloading is that these functions do pretty similar thing, but slightly different. So in the caller functions, we will do the same thing with slightly different parameters. That's why we have the same function name. But since the parameters are different, then we have to implement these functions in a different way. Okay, if the difference is only the parameter in the implementations, then we can use a template. Okay, but it could be more than just the data type. I mean, in the implementations, instead of star debug, we can use some other messages. Okay, so depending on this parameter, then if we do something different in the implementation, then we have to implement different functions for different parameters. Okay, so this is a function overloading. Then we will use this one later. Here's a copying binary trees. So we implement this operation recursively. First, copy left and right subtrees recursively, and then merge the subtrees with a root node. That's it. So let's take a look at the first function. So as I said in the previous slide, we have two functions with the same name, but with different parameter types and return types. Okay. So first one, we get one tree node pointer original. So this is not the binary tree pointer, it is a tree node pointer. And then we check if this original is null or not. If it is null, then we return null because we don't have to copy anything. Okay, if it is not null, then it is pointing something. Okay, then we have to copy something. So if it is not null, then we have to allocate memory space. So now temp is pointing one memory space. And then great part is just checking if this allocation is successful. Okay, let's assume that it's successful. And then we will call copy function one more time. And at this time, we will call copy a function passing original's left child pointer. Okay, and then temp left child will get that. And likewise, temp right child will get the result of copy functions where we get original right child. Okay, so by these two statements, we will copy the left subtree and the right subtree. Okay, remember temp is a pointer to one new node, right? And the temp has two pointers and one data field. And the temp left child will point the left subtree, and right child will point the right subtree. And then data will copy the original's data. And we return temp. Okay, so this is a recursive solution. Okay, let's take one step further. So let's try the first copy function here. Okay, temp left child is copy original left child. So if we call this function with this parameter, then in the functions, okay, then original will point the root node of the left subtree. Okay, and we will do this again. In the second copy functions, if we call, then in the functions, the original will point at the root node of the right subtree. Okay, so if you are not familiar with recursive solution, recursive implementation, then this might be a little confusing. But once you are familiar with recursion, then I think this is really simple. Okay, so now the function implementation in this slide is about the tree node pointer, and it will return tree node pointer. And when we get a binary tree pointer, then how should we copy? Okay, then in the second implementation, okay, in the second function here, we get the binary tree pointer, and then root. Root is the current class's root. Okay, this root will get the return of the copy functions, and this copy with the source root. This copy means the first implementation of these copy functions. Okay, because source root, the type of source root is tree node pointer. Okay, so this copy means the first one, the upper implementation. Okay, and then the first implementation of the copy function will return the tree node pointer. So root will get that. In this slide, we have an implementation of testing for equality of binary trees. So given two binary trees, we want to check if they are equivalent. Okay, so the algorithm is quite simple if you understand the recursions. okay, is quite similar to the copying operation. So first, we compare two root nodes, and if they are equivalent, then we check left subtree first and then the right subtree. Okay, as we have seen in the copying operations, we have two implementation of equal functions. And the first one is about checking two subtrees, and the second one, I mean the green one, is actually getting one binary tree pointer. And in these functions, we call first one. I mean in the green function implementations, when we call the equal, this equal is actually blue one. Okay, so we pass two tree node pointers. Root is a tree node pointer, and the second root is another tree node pointer. So this is a function overloading. So from this green function, we will call the blue one. Okay. So in the blue one, we get two tree node pointers. Okay. So these two pointers are, in general, are pointing to subtrees, respectively. And this is not just a left subtree and right subtree. Okay, the first is pointing a one subtree from the first binary tree, and the second tree node pointer is pointing a subtree from the second binary tree. Okay. Okay, so in this blue functions, the first we check if both are null. If first is null and second is null, then they are equivalent. Okay, then we return true. Or if first is not null and second is not null, and they are pointing something, okay? And then now we check the root node of the subtrees, okay? So we check if first data is the same as second data. Okay, if that's the case, then okay, the root node of these two subtrees are equivalent, the same thing. Okay, now we actually call equal function twice. Okay, so these equal functions are actually, we call the blue one, okay, because we pass two tree node pointers. And the first, when we call equal functions, we pass first the left child and the second left child. So, we want to compare the left subtree. Okay, so are they equivalent? Okay, and then next, we want to compare the right subtrees. Okay, so in this blue implementation, we have two parts. The first one is checking if both are null, and second one, after these all operations, in the second one, as long as they are not null, both are not null, then we check the root node first. I mean, in this figure, we check v, okay? And then by calling equal function twice with passing the left child and the right child pointers, then we check if left subtrees are equivalent and right subtrees are equivalent. If the root nodes are same and the left subtrees are equivalent and right subtrees are equivalent, then we return true. Okay, this slide is a little easier implementation of this equal functions. So this equal function is corresponding to the first equal implementation in the previous slide. Okay, so we get the two tree node pointers. Okay, and then first we check if both are null. Okay, then we return true. Else, if first is not null and the second is not null and the first data is the same as second data, and then the left subtree is the same as the left subtree of first is equivalent to the left subtree of second tree, and the right subtree of the first tree and the right subtree of the second tree are equivalent, then we return true. Otherwise, we return false. Okay, so this might be a little easier than the previous slide implementation, but basically it does the same thing. Okay. And by the way, we need the second implementation of equal function from the previous slide. Okay, now let's talk about insertion operations. Okay, so we can insert a node somewhere in a tree. Okay, but we don't know where to insert. There are some algorithms, okay, but to think of this insertion in a simple way, let's just add a node at the leftmost leaf of the tree. Okay, so given a binary tree, then we will add a new node at the leftmost leaf node. Okay, so this is one simple implementation. So this is not general insertion function for binary tree. Okay, this is one simple extreme case example. Okay, so the data is just integer. And now in the functions, we allocate memory space for a new node. Okay, PTR is pointing that node, and we copy the data to the data field. Okay, so the PTR data gets num. Okay, and then PTR left child and PTR right child will be null because we are adding this node at the leftmost leaf node. So now this new node will be the leaf node. Okay, and if our current binary tree is empty, then the root should point while PTR is pointing. Okay, and else it means root is pointing something already, so we don't have to touch root. Okay, root is pointing the root node of the tree, and we have to find the leftmost leaf node. Okay, so we declare one tree node pointer cur, and cur starts from root, and cur will move to the left child as long as cur left child is not null. Okay, and then we have a semicolon at the end of this for statement. It means we don't do anything iterating this loop. Okay, so at the end of this for loop, now cur is pointing the leftmost leaf node. Okay, so now cur left child should point a PTR. That's how we add your node. Okay, again, this is not general insertion function. This is one really simple extreme case. So now let's assume that we have a binary tree class, and then we have all the implementations. Then in the main function, we can try many different experiments. Okay, first we declare tree1, tree2, and tree3, and they point the memory space for a binary tree. Okay, and then tree1 will insert 3 and 1 at the leftmost leaf node, and we implement another simple insertion functions, insert node right. It means we will add a new node at the rightmost leaf node. Okay, and then tree1 will print, and tree2 will insert 3 and 1 at the rightmost leaf node, and then we print. Now we can check if tree1 is equivalent to tree2. So tree1 will call its own equal function passing tree2. Tree2 is a bin tree pointer, okay? So that we will call the second implementation of the equal functions, and then it will call the first implementations and recursively. So if tree equal returns true, then they are equivalent. Otherwise, we print out not equal, okay? And then we delete tree2. Now tree3 will copy tree1, okay? So tree1 is a bin tree pointer. So again, we'll call the second implementation of the copy function, and in the second, in that functions, we'll call the first implementation of the copy functions. Okay, and then we print out, we call tree3 print functions, and now tree1 will call equal function passing tree3, and they should be the same, right? We just copied, so the return value should be true. Okay, then we'll print out equal. That's it.